particle P of mass 2 kilograms is resting on a rough horizontal plane. It is connected to another particle Q of mass 3 kilograms by a light, inextensible string that runs through a smooth pulley, and the pulley is fixed at the end of a plane. Particle Q is hanging freely and the string is taut. So here's particle Q. Let's draw in some of the forces. It has a weight of 3g. Here's particle P, which has a weight of 2g. It must have a normal reaction as well. Okay, what else do we have? Particle P. Find the magnitude of the acceleration of the particles and hence how far P travels before coming to rest, given that Q hits the ground 2 seconds after it's released from rest. Okay, so what we're assuming here is that it's released from rest and it's obviously going to go that way. After 2 seconds, this one's hit the ground, so that P is still on the table, but the string is now not taut, it's a loose string. We're going to say that essentially the string is snapped because there's going to be no tension here. And then how far does that go before coming to rest? Assuming that it never actually reaches the pulley. The pulley's far enough away for it to give it enough time to stop. Okay, so let's add in some of our other forces. I have tension in the string here, and I have tension in the string here. We know that the tension is the only force acting horizontally to particle P, so the friction must be acting to oppose that. We know that the friction is 0.2 R, because we know that the friction is going to be a limiting friction because it says it's accelerating, it's moving, so F equals mu I in this case. And I think that's all the forces that we have right now. Yeah. Okay, so let's see if we can find the acceleration in the system, because we're going to need that if we're going to somehow use, I can definitely see we're going to use SUVAT to do this question, because we're trying to find out how far something travels. The acceleration is constant whilst the tension and the friction stay the same. So let's work out, first of all, we're going to resolve the vertical forces of P, and we know that it's an equilibrium, so we know the up forces equal the down forces. The up forces R and the down force is 2g, so we know that R equals 2g, which in turns means that we know that this is 0.4g in total. So now we can take the horizontal motion of P, and we know that the resultant force equals mass times acceleration. The resultant is going to be T, take away 0.2R, but R's that, so it's 0.2 of that, so it's 0.4g, and that equals a mass of 2 times by some acceleration, and we know that this particle is going to be accelerating in this direction, and we know that this particle is going to be accelerating in this direction, and because the string is inextensible, they're going to have the same acceleration. Okay, so let's work out, let's make T the subject of this equation, because I think we're going to use that in a second. So this is going to be 2a plus 0.4g, because we're now going to look at the motion of the vertical motion of Q, and we're going to take down to be positive, and it's going to be the resultant force equals mass times acceleration. The resultant force in this case, taken down to be positive, is 3g take away t, and the mass is 3 and the acceleration is a. So in this case t is going to equal 3g take away 3a. Therefore, let's move over to here. I'm going to run out of space, so I'm going to start moving across a little bit. Therefore 2a plus 0.4g is going to equal 3g take away 3a. So I'm going to have 5a on this side, and 3g take away 0.4g. 3 take away 0.4 is 2.6. 2.6 times 9.8 is 25.48. So that's going to equal 5a. If I divide by 5, I'll find out that the acceleration is 5.096, and that's an exact answer. So I know that the acceleration of both particles is 5.96, but this is only true for the first 2 seconds of the journey, because it takes 2 seconds for this particle to hit the ground. As soon as this particle hits the ground, the string isn't taut anymore, so this tension disappears. Okay, so the tension will disappear after 2 seconds, and we will just have the friction, which will slow particle P down. So I'm going to work out the acceleration of P, or the deceleration of P, for the second part of the journey. So after 2 seconds, okay, we know the acceleration changes because the forces change. If the forces change, F equals ma, remember. So as F changes, A has to change, so we have to recalculate A. After 2 seconds, resolving the horizontal motion of P, the resultant force is going to be minus 0.4g, and that's going to equal the mass times by the acceleration. So it's the same line here, but t is now being removed. So we're taking right to be positive, so the acceleration is going to be minus 0.2g, which is minus 1.96. So the acceleration in the second part of the journey is minus 1.96, so a deceleration of 1.96 to the left. Therefore, we just need to, now we can use SUVAT to work out the speed with which P hits the pulley. Oh, sorry, the speed with which, let's read the question again. Find the acceleration of the particles, and hence how far P travels before coming to rest. So we're trying to find the distance before it comes to rest. Okay, so we are now doing kinematics of particle P, and I'll do S, U, V, A, T, and for the first 2 seconds I've got an acceleration of 5.096. We know it starts from rest. We don't know how far it travels, but we can work that out. I'm running a little bit out of space here. Let's see if I can. Yeah, I can do this up here, I think. So I'm going to have. Let's start with kinematics of the next 2 parts of the journey. Kinematics of P, S, U, V, A, and T. So after 2 seconds, we know that the acceleration is minus 1.96, so I'm still taking right to be positive. I know that U here is the final velocity of this part, so the velocity after 2 seconds is V in here, but it's U in here, and I know it comes to rest. So as soon as I get this U, I'll have enough information to get S, and I have enough information already here to get S. So let's work out S in the first part, which we're going to use. S equals ut plus half at squared. S is going to equal 0t plus a half 5.096 times by 2 squared, which is 0.5 times by 4 times by 5.096. So that gives me an answer of 10.192. So we know that this must have started 10.192 meters from the ground, because that's when that's how far it travels. It travels the same distance in the 2 seconds before it hits the ground, and then everything changes, all the acceleration changes. Let's work out the final velocity as well. V equals U plus AT, u is equal to 0, so this is just going to be 5.096 times 2, and I reckon I could probably do that in my head, so that's going to be 10.192. So this is going to be 10.192. I don't want to ruin the whole video by getting that wrong, so let me just quickly check it. And then again, I'm running out of space, but I can use v squared equals u squared plus 2as in this part to work out this. So let's do that up here. V squared equals u squared plus 2as. V squared equals 0. U squared equals 10.192 squared. Take away 2 of these is going to be 3.92s. So I can work out that s is just going to be 10.192 squared, which is 100 point something, divided by 3.92, which gives me an answer of 26.49. And therefore the total distance travelled equals 26.4992 plus 10.192. which equals 36.7 meters.